quick intro. I'm going to explain monads, but don't panic. After this sentence, we won't use the words monads, monodic, monoid, functor, endofunctor, or even category. That's not because these words aren't important or learning about them isn't interesting and enriching. It's because you don't need to know these words to understand this pattern. I think the terminology can be off-putting, which is a deep shame because this pattern is chef's kiss. When programming, we regularly take a value and perform some operation to get a new value. In fact, it's pretty much all we do, right? Let's say we have the value 5, which is an integer. We could square the value, which gives us 25, which is still an integer, or we could turn the value into a string, which is still 5, but is now a different type. If we turn these operations into functions like this, we can think about these functions as taking something of type t and returning something of type u, even if t and u are the same type. We usually write Rust here, but I'm briefly going to swap to using TypeScript to explain this next bit because Rust simply won't let me write the code this way. But let's say we have a function that returns either a number or nothing represented by null. The function isn't important, it just represents that some functions, by their nature, may need to return different types depending on what happened when they were called. But our functions, reproduced in TypeScript here, only take numbers. This means we can't just pass a variable that might be null into the functions. We need to check if the value is null and only pass it in if it's not. This is a process called narrowing. We can do this with branching. TypeScript is smart enough to know that it's impossible for the value to be null in this branch, so this works. But it obviously reads terribly and adds a lot of boilerplate if we have to do this often. The next logical step is, if we're just checking for null, we could abstract this to a generic function, which in TypeScript would look like this. Here, we're passing our function that takes t and returns u into another function that takes t or null and returns u or null. If the input isn't null, we run the passed function, otherwise we return null. Now we can reuse this code a lot more easily, but there's still a lot of toing and froing. Also, none of this works in Rust. There's another logical step we can take though, one that lets us get back to Rust. One that's also a little more fluent, if you will. At the moment, we're dealing with a value that could be type t, or it could be the very concept of nothing. These are two separate types. What if we wrap these types in a container that could hold either t or nothing? We'll call our container m for reasons. We'll call it m for reasons. So we have our container mt or nothing and our functions ft returning u. We can give our container a way to take that function and return a new container, mu or nothing. Rust actually has a built-in type that already does this, but to explain the pattern, we're going to reproduce it. We'll start by creating an enum called maybe, because maybe it contains a value, or maybe it contains nothing. We'll then give it a method that will map from maybe t to maybe u using the provided function ft returning u. This method is functionally identical to our if not null function we wrote in TypeScript, but operates directly on an owned version of maybe. Now when we call our Rust equivalent function to divide two numbers, we'll get a maybe i64 back. We can map the maybe i64 using square. Because our square takes an i64 and returns an i64, using it on maybe i64 returns another maybe i64. When we use toString, which takes an i64 and returns a string, our maybe i64 turns into a maybe string. That's all well and good, but it seems like this hasn't saved us much over what we were doing with the if not null in TypeScript. Where this pattern shines is that in TypeScript we were dealing with a value that could have two types. By encapsulating it in a container, we're only dealing with one type, which means we've built ourselves a fluent interface for managing our data. This means we can inline all of our maps and it becomes far more readable than if we'd inlined our function calls. For what it's worth, this pattern works perfectly fine in TypeScript too. By now you've probably worked out that our maybe type is us creating a less fantastic Rust option. Our containers could be more flexible than just t or nothing though. It's perfectly reasonable for your container to potentially hold multiple things. Let's say we have a container that could hold types t or v. This container should not only be able to take ft returning u, which will give us a container potentially holding u or v, but it should also be able to take fv returning w, which gives us a container potentially holding t or w. A good example of this in Rust is the result enum, which holds an OK variant of t and an error variant of e. However, we can't just hand over ft returning u or fv returning w and hope for the best, because what if both variants hold the same type? It's not unheard of for both variants of a result to be the same type, either a unit type or a string. I mean, it's not ideal, but it's not impossible. Rust result type has separate methods for changing the OK variant or the error variant, the former still being map and the latter being map-er. I'm sure I've made some hackles rise in my description of this pattern, so I do want to explain there are some specific rules that make this pattern what it is. It's not just any old container. Firstly, for a given container, a value represented as a type inside that container should be convertible to that container without changing its type. In our maybe example, as well as option and result, we simply pass the value to one of the enum variants so the inner value doesn't change. Second, there needs to be a way to apply a function to the inner type such that if you apply ft returning u to a container potentially holding a value of t, then you get a container potentially holding a value of u. In our maybe, applying ft returning u to maybe t returns maybe u, regardless of whether it contained a value of t or not. In some languages, the rules are a little stricter and the pattern works very slightly differently, but there are plenty of videos that can explain the specifics for those languages in more detail. I just wanted to explain the basic pattern in an easy to digest way because I think it's an extremely cool pattern, one that's surprisingly crucial to how Rust works. This pattern can significantly reduce complexity, removing a lot of cognitive overhead when reading and writing code. Rust is filled with this pattern and, in fact, wouldn't work as a language without it. We just don't use that name because it feels overly complex. I hope I've aptly explained this pattern without all the scary words, but if you do want to learn more about this pattern, warts and all, there's a lot of great YouTube videos out there. I'll recommend some in the description of this video. If you enjoyed this video, don't forget to like and subscribe. If you really like the video, you can become a member of the channel or join the Patreon. See the description for more. Next time we're going to talk about dependency injection, which is crucial to building complex yet maintainable software. I hope I'll see you then.